Hey everyone, and welcome to the Information Bottleneck. I'm Ravid, and as always, I'm joined by my co-host Ellen. And today we have really exciting guest, Chieh-Hsin. I hope I pronounced it correctly. A staff research scientist at Sony AI, and also a visiting a professor at the university at Taiwan. Hi, how are you?
Hi. Yeah, thank you very much for having me here. Nice to meet you guys.
And today we are going to talk a lot about diffusion models. You recently wrote a book that called The Principle of Diffusion Models, together with Stefano Ermon, that some of you may remember from a previous episode. And this is quickly becoming a go-to reference in the field. So we're going to talk about it a lot. So let's start from the beginning, okay? Maybe what does it mean, diffusion models, and what does it, how it's different from what we all know as um, regular autoregressive models?
Yes. Yeah. So yeah, about is that good now?
Yeah.
Yeah. So about the book, yeah, I mean, because I have been giving different invited talks in different scenarios. I have met a lot of people from different background. But for different models, I mean, itself already, I mean, until now it has I mean, it is 7 years old almost. And there are tons of papers with different names. Actually, they are doing quite similar stuff. But for beginners or for someone who just new to the field, it's very hard to pick up every paper and dive into every single details and especially if you are a beginner, it's very hard to know what is important, what is you should know to do research or do your own study. So because of this, I think we should have a really fixed and principles reference that people can just okay, this is the only thing that I need to read to know about diffusion models. And you don't need to check back to tons of papers and then to understand the connection between dot and dots. Yeah, I mean that is quite challenging for beginners. So because of that, I mean we want to have a standardized book.
Do you think so? I feel that a lot of times, people are calling the same thing in different names, right? And there are a lot of papers that say basically the same thing, or have very similar methods, but somehow look on it from different perspectives. Maybe. Do you think this is the case also in the diffusion models field?
Yeah, definitely. For diffusion model itself, if we need to say, it actually dated back to the 2015 paper. Uh, at that time, it is from a physical perspective. But it hasn't been noticed by people until 2020. I mean, the so-called the DDPM paper from Google. Um, and also simultaneously, from Stefano's group, Yang Song himself, they have a different counting point to the generative model, which is now similar to the diffusion model, which is the score-based model. And actually they are quite connected. But if you don't have a deep dive into the math or sit down very think very carefully, it's really hard to connect these two dots. And not only this, say for example, the generative model itself, I mean one of the most important generative model is the normalizing flow. It actually has a long history back in 2015 around. And it also kind of gradually developed to diffusion model, which is now people understand it as a flow matching. So there are actually three different perspectives. Variational one, which is a DDPM style, and the second one is the score-based diffusion model, and the third one is the flow-based diffusion model. So I mean we want to
So
make it clear.
Okay, so let's start from the beginning. Okay, like what is the most general framework that you can describe it?
Yeah, so I think I should talk about what diffusion model is, right? So and especially like what the generative model is. So for generative model, we want to do the generation and do the sampling from a very complicated data distribution. And what we can do is just use a neural network, and then to uh bring the noise back to the realistic samples, and we want to make the realistic sample as close as to the true data. And the diffusion model is one of the ways of doing that.
Maybe that
You
wait,
instead of doing this kind, yeah,
maybe let's start from the beginning. Why we actually want it? Like why we actually want to sample from very complicated distribution? Maybe let's start like what does it mean even like good generative models? What does it mean? Like what we want from good generative models?
yeah, that is a good question. So to have a good generative models, we definitely need to have a good quality. Just like ChatGPT, we want to have the correct answer that in our mind. Or like for image generation, we want to have at least photorealistic image. Well, that is important, the quality. And the second one is how to make. I mean, in terms of the engineering perspective, we want to have the model training easy and stable, and do not have too much ad hoc techniques. We can just like the training runs. So that is one of the important factor. The third one could be we want the general model to be more controllable. Say if we want to generate a cat image with some features like wearing a hat, for example. We want the model to really capture the user intentions, and that could have tons of application that we have already seen, like stable
But
diffusion, this kind of stuff.
we also want like generalization, right? We don't want that it would just mimic the training data.
Definitely, definitely. We don't want to just memorize the training data. Otherwise, it's just, yeah, generate something that we already know. So yeah, we kind of need to accumulate a lot of training data, but want to have some inductive bias to do some generation. I mean, new content creation. So yeah, that is quite important.
So in classification and discrimination, it's easy, right? Like to quantify generalization or quantify quality. Even if you don't have true labels, you can try to quantify it somehow, right? In with different judges. But how are you going to do it in generative models? How you quantify if your model is good in practice?
Yeah, so in different data type, it has a different if in terms of academic papers, there are tons of different metrics. Say like how to test distributional wise similarity between the generation and the your data, which is called the FID, kind of Verschuert distance in the latent space. And you also want to check whether you are really memorizing the training data. So there are some a memorization index, like whether you just copied the training data itself. And yeah, I mean, in terms of diversity, there are also different metrics uh in image, and for different data type, it has different this kind of different evaluations to make sure your quality is good and it's really generates something new. So
So, do you think that there's any advantages of diffusion as a technique over autoregressive techniques for image generation?
yeah, I think that is a good question. Yeah, so um in terms, I mean, for diffusion model, it is more controllable. The diffusion model generation is like you go from pure noise and then gradually cleans up the noise, and then you can get your generated data. So you can actually steer your generation in the middle by your prompt or your intention and whatever additional condition. Then you can detour the trajectory to something new. And that is not so easy for autoregressive model. And at the same time, you can also kind of refine your generation, like by slightly going back and then do this kind of refinement again and again. So
Yeah. And I want to quickly highlight like the communities of people in the image generation space that have taken diffusion models and built, with comfy UI or automatic, like tons of extensions doing exactly what you're describing, adding control and even implementing things like regional prompting, and then like the entirety of control net, right? And that whole body of work. So I've seen exactly what you're talking about firsthand, and yeah, it's very strong. Diffusion models are also faster in practice most of the time, right? Would you agree with that too?
Yeah, I think that is a tricky question. Like initially, diffusion model is known to be very slow because it needs to have this kind of refinement and gradually denoising process to get a new generative sample. But nowadays, like people have pushed a lot uh, to make the different model generation faster. One of the important direction is like this kind of generation is actually describing by some like a sample wise trajectory. So it is like differential equations, like particle movement between one pure noise to your data. And there are tons of like math literature that you can borrow from to make the generation faster. And yeah, there are other like a trend, like how to like distill or like compress your different model, your pre-trained different models, which needs hundreds of thousands stack to like 1 or 4 stacks, for example, which is called distillation. And yeah, there are other new like different motivated frameworks that can do faster generation. So short answer is like I believe now diffusion model or like diffusion motivated models is capable of like fast generation and controllable generations.
Let's try to go step back and to understand or like to describe like the different terms, right? Like you have diffusion models, score-based models, only things that are related. Maybe you can help us to understand it, like how they related, what does it mean each one of them, like um are they different for different cases? Like yeah.
Yeah. So yeah, I think like for it is I think it is good to step back even more to like what people have already been doing for generative models. Like people like say again, like what people did is like they just use one function to bring the noise to new generation. I mean new sample. But for diffusion model, it is like a gradually process, and this gradual refinement process can be viewed at a different perspective. One of them is the variational based, which means like when you go from the data to pure noise, you are adding noise. But in the variational one, you try to reverse this kind of Gaussian adding noise process by like cleans up the noise step by step. That is the variational perspective, which is quite similar to the variational autoencoder with the fixed encoder, for example. And the second route is the score-based, which is one, like pioneered by Stefano and Young's group. What they did is, say like the score function is actually the gradient log density, which telling you how to move toward a high, most like a likely region of the generation. So it is a vector like pointing toward like a high density region, and you can just use the score
High
function.
density,
Yeah,
what is the score? Like you have some score function, right?
yeah.
So what is this score
So
function?
yeah, so score function is like a vector, a direction that pointing toward where you can generate like a like high probably, good looking samples, for example. And you can do the sampling just in the gradient ascent manner, like because it tell you where the point cloud is located, so you can just move toward that region. That is a score-based perspective. And the flow-based perspective, which is originated from the normalizing flow, which is just like using piles of like a invertible mapping to gradually bring your data toward noise or like a reverted. But if you move like a view in continuous time, which means like infinite piles of this bijection map, actually the dynamic is just like a differential equation. So it's just like a different cutting point toward the same foundation. Yeah.
So What are the connections between the three?
Yeah. So in terms of the connection, there are actually two perspectives. The first one is how they shift the from distribution to distributions. And the underlying principle of the distribution to distribution shifting or transforming is actually literally the change of variable formula that we have learned in the calculus. So these three different origins can be viewed in a unified way of this kind of density evolution of change of variables. And the second thing is even though they are originally from different perspectives and have different training objective, but these different training objectives are simply related by some simple math formula. So it is just a very neat story, especially for the Gaussian diffusion.
And so what is
Yeah,
that
unlike this,
Gaussian diffusion?
the Gaussian diffusion is adding Gaussian noise and then gradually denoise it. Like people call it diffusion model, but diffusion model actually have two versions of it. The first one is continuous diffusion or the Gaussian diffusion, which people usually use it for the image or the continuous data generation. And the second route is discrete diffusion, where people use it for the text or protein, this kind of more discrete features data generations. And the book is about the continuous diffusion, but the discrete diffusion also have a quite similar structure.
So, you talk about the partial differential equations and denoising earlier, and how there's like a bunch of math around it for improving things. You're talking about things, with names like Euler adaptive and Euler and other names like that, right? Am I correct? Kind of.
Yeah, actually, there are tons of this kind of math jargons. But to understand diffusion model, you don't need to really dive into each details by details. So correct, yes, there are lots of math, and it is like a quite math supported generative models. But on the other hand, you don't need to really understand everything. Every math underlying it. So.
Well, what I'm more asking about is I've noticed it's similar to like the LLM sampling world, and so we've even submitted like a workshop in the past called SDDL, sampling, denoising, diffusion, and logic processing. And what I'm wondering is, do you think that the source of like diversity in diffusion models is primarily in the weights, or do you get control of it at that partial differential equation layer, or is it like the CFG, like context-free guidance, or where's your opinion on kind of the best knobs to tune for improving like diverse outputs?
Yeah, I think that is a good question. So definitely CFG can matters somehow. I mean, just step a little bit. Like CFG means the classifier free guidance, which means which means you can input your prompt and then drag your generation trajectory towards the different different direction aligned with your prompt, and it has some weighting to decide how much you want to push toward that prompt directions. And if you push too much, then it could decrease the diversity and it can kill the samples. But sometimes the weighting can help your generation quality to get better. So it is a trade-off, and CFG can matters in terms of the generation diversity. And people now believe you scale up, you prepare tons of data and especially good quality data, so you can have quite diverse samples.
Then I'm also familiar with the concept of like prompt weighting, so I can upweight a token that I want really bad in my image like 2 or 3x. And I love this feature. I wish LLMs had this. I desperately wish, but it also occurs to me that this is horrible for alignment and safety, because I can say I want a bomb with like 10,000 multiplied or something for generating text. What's your take on prompt weighting and manipulations like that?
Yeah, I think it has I mean, it depends on how you use it, or like, I mean, what's your target people? Like, if you want to really have a huge control, like huge full control of the generation, I mean, that is a good thing, right? You can like freely control it. But if you want to do some like safety, I mean, safety like kind of guard, then you actually can design your model uh, during training to remove that particular prompt. It is like a negative prompting in the CFG. Like you can push away toward that direction, but you can also push toward. I mean, just depend on the vector directions. Yeah.
How you can do it in practice? Like you calculate the vector direction of something that you want, and then push along this direction. Like you get like you're trying to get the gradients along this direction.
Yeah. So it's more like you can have the positive prompt, and you also can have the negative prompt. For a positive prompt, you can like go more along the positive prompt. I mean, which is the user intention. But for a negative prompt, you just like do the subtraction, like negative direction. So you can like go away from that. So that is a simple trick, but sometimes it is quite effective. And yeah, people use it to prevent this kind of dangerous iterations, or like even for like to avoid the memorization.
And what do you think in general about like combine images and text? Let's say specifically in diffusion models. Do you think this is something, because like I don't know, like a priori, I would think that you need different types of noise and different types of like regularization and normalization and all this stuff. Do you think it's possible to combine them in a good way? Do you know actually like models that do it in a good way?
Just to make sure what you mean by combine, like, do you want to user provide the prompt to generate or something else? Or
Let's assume they want to learn end-to-end diffusion model that combine both images and text. Do you
okay.
think do you think we should have one like noise types, or I don't know, something that somehow will treat differently these two domains?
Yeah, I think I guess it's more like a multi-model style, right? You want
Mhm.
to, yeah, generate from one modality to the other, or like there are multiple modalities in one hand, but you can also want to generate the other, like multiple modalities, like text, music, this kind of different combinations. So I think um the simplest one is like we just bring everything into the same common latent space, the same features, and then we do whatever like different modeling or whatever modeling in the latent. So we can kind of get different sources, I mean different conditions from text or from image, and then generate the other things. And yeah, I think there are tons of big techs and lots of papers are doing that, like multi-model different models, for example.
And do you think like what types of, do you think I don't Gaussian noise is the best that we can do, or do you think like the future is let's construct specific types of noise that will be good for different domains, different tasks, or whatever?
Yeah, it could be like say I tend to believe like the text information and the image information, I mean they are not carry the same amount of like signal. So perhaps we need to do more denoising, or like adding more noise to one specific like representation text or whatever, and do less on the other hand. So I think there are some like design space that we can definitely explore. Yeah.
Oh, so when you worked on diffusion models, has there been any very surprising results that have come out from any of your specific work, like very counterintuitive stuff? I know we were talking earlier about that Mirage paper that was extraordinarily counterintuitive to us. So, have you seen any, truly surprising things for yourself?
Yeah, actually, I wouldn't say it is like really counterintuitive, um, but it's more like okay. So like like let's talk a little bit like step back. different model is very slow for generation at the very beginning, and people push it a lot to make it fast. One type of the model is called a flow map, which you directly learn anytime to anytime movements along the diffusion generation trajectory. So you can directly go from the pure noise to the clean generations. And back in 2 years ago, there was one of my intern working with me, which is one of the earliest work to do this kind of flow map, called the consistency trajectory model. So at that time, we push a lot to make the one-step generation of different model happens, but the quality is so bad. I mean, if you just do one step, the quality is too bad. But we found that's okay. Perhaps you need to borrow some what people have already been built in the generative models community, like the GAN. Then it can help you to boost up the generation qualities. So it is kind of counterintuitive in the sense that in my educational guess, it is quite natural and quite reasonable to do this kind of one time to the other time jump directly. But it turns out in practice, the quality is not that good. So yeah, so we need to borrow something else, and yeah.
And then quickly, just going back on that noise question, while I'm thinking about it, it seems interesting to ask about alternative types of noise, because I didn't realize there were there are names for all the different types of noise, like white noise, pink noise, and they all have various mathematical properties that people probably in the radio side of things care a lot about. As it turns out, I was doing game development at one point, hobbyist game development in roguelikes. I don't know if you've ever heard of NetHack. NetHack is actually kind of an important benchmark in some reinforcement learning communities for playing. But I like designing games similar to NetHack, like these little terminal dungeon crawlers, basically. And one of the fun ways that you can start creating kind of diverse levels that don't just always resemble these caves and hallways that most games like NetHack do is to implement noise into generating, basically, is this a door, or is this a open space, or is this a wall? And I've personally experimented with significantly different types of noise to get different types of maps. But do you think that denoising images has any kind of properties where the changing that noise pattern in some particular way, maybe even something where at training time you had different noise patterns associated with different control or something? Is this something, have you ever seen work like that, or is this interesting to you? Or
Yeah, it's definitely interesting. Actually, it is a good question. Especially, let me bring one example. For the video, if you want to use a diffusion model for video generation, a video, you can think it as a sequence of image, just sequence of frames. And different frames actually have a different importance. We shouldn't, for a video generation, we shouldn't treat each frame as the same level of importance. So perhaps for some important frames, the main character is there, we should craft a specific noise for denoising. But for some less important stuff, we can just whatever noise. So yeah, noise is very important, and especially for the video level generations.
And what do you think the future will look like for video generation? Do you think we'll see agentic flows? Do you think we'll see more diffusion? What do you think is the 5 or 10 years from now?
Yeah, I wouldn't say 10 years. Yeah, it's too far for me.
Let's start with year 1.
Yeah, so I would say how the video generative models, video diffusion, be interactive in real time with the agent. People have a different name called the word models. like it is a quite challenging topic, and in my opinion, it should be as important or even like more like it could have more like profound impact than the LLM, like because we are using AI to model the real world, and the real world should change simultaneously. Like if one person do something different action, then the total environment would change. But like how to apply the video generation model or like video diffusion model in a good way with this kind of agent in the real time, and also make it to have a long time consistency. I think it is a big like big challenge, and I think it should happen quite recent. So
But do you think we should have like a text understanding? At the end, we are describing physical world, right? We are describing the physical world, and like Anto, in principle, we need to understand if we want to change something in the image. That's fine, but if not, like we don't need something like that. Do you think this is a requirement to understand the world, like to understand how humans looks on the world, or split up the two problems?
yeah, I think understanding and the generation sometimes are quite tied. Yeah, if you have a good understanding, or you can turn it into a better representation, sometimes it can make your generation even better. So in my opinion, I'm not thinking in the like two different tasks, but we should consider it at the same time.
And one more question. So do you think that these models will be so heavy, like compute demanded? Do you think like we'll still see at the end, I don't know, like how many people can actually like train diffusion models or like flow based models or like all these generative models, especially for images, right? Like you can train small models for text, and they are for specific task. It looks that they are quite okay, but we don't see it for a generative model for images. Why do you think is that?
Yeah, I think now it's an era of like training huge gigantic models. Because currently we have like a sufficient good enough data that we can use, and we just scale it up. But I mean, as you mentioned, like it's like quite challenging for some institute to really train like huge models by themselves, like text to image generated models. Not every lab can afford it. So I mean, one of my research concern is also like how to make this kind of big models or like this kind of huge general models training be heavily reduced in terms of the compute. So yeah, I think that is like people goes the huge models training, but at the same time, I think it is equally important to make it lighter and more task specific.
So, do you think we'll see more efficient models, smaller models, model that will require less data during training, during inference? What do you think we will see next?
Yeah, so I think like there are several tricks that we can play around. Especially, let's assume like we already have the access to all of these open source huge different models. We actually can recycle this kind of big models from like a big tech or big lab, and then do some sort of distillation or like a kind of like there are tons of tricks that we can do, like distillation, providing some good initialization for your small model training, and it actually can already cut off a lot of training budget. Especially if you want to use it for a specific task, you don't need to have a huge model. So yeah.
And while we're talking about optimization techniques, what are your thoughts on things like quantization and then early exiting layers? I'll especially remind that one of the major versions of Stable Diffusion XL, actually had, they call it in their world clip skip, because clip is the name of the, I think, text encoder. And then they have you use the second to final layer instead of the final layer to exit from, which I always thought was really weird. But what's your thought on techniques like that?
Yeah, I think like definitely if you want to have a commercial level of like this kind of big models, you need to put that up a lot of like engineering like method to make it work and work at a good way. And I tend to believe there are more secrets that we can make this kind of training even better. So good to have. And it's more like good to know because we can just like use it for our use case. So yeah.
Let's
And
talk
then
about if you like world models. Diffusion models. You can look on them as world models in some sense, maybe like but not explicit world models. And we all the time we have these discussions in text and world models. Do we need explicit versus implicit world models? Like, do we need to train them in a different way? Um, does it can it make it better or worse? Like for other types of tasks? What is your take on world models? Or like maybe let's start with your definition for world models.
Yeah. So that is a good question. Like different people have different opinion about the word models. Alice, I think it should have a like it should like react like immediately toward the agent reactions, and it should have the long term consistency. Especially like some like this kind of video model or like this kind of word models sometimes kind of mimic or kind of provide some proxy to the real physical law, but it turns out it is not quite. Um, to my opinion, it's okay, but like if say for example, if I want to pan fry the egg and like walk away 10 minutes and then coming back, the egg should like get crazy, right? But whether this kind of word model can have this common sense understanding or like a reaction of the agent, I mean that is a quite interesting research direction, and it should have, the word model should have this kind of features. Yeah, because it is like just reflecting what the real world is.
So do you think that there's underlying understandings of physics that are kind of possible to get in the weights of a sufficiently large size diffusion model? And I guess related to that, it seems that the world still kind of waits for, at least in the image generation space, a truly large image generation diffusion model to come out, like one that's also powered by a very powerful, like large text encoder. Is there reasons for that? Is it just because it's so expensive to train them at that size?
Yeah, I think the compute definitely is one of the reason, and also the quality. Data quality is another reason. For image, it is easier to get high quality data. But on the other hand, like if you want to do the video or other sources, it is quite challenging. If you just scroll from the YouTube, usually you will get kind of dubious, or like you will be sued by someone. So like how to get a high quality data and like the compute is not affordable by everyone. So
But I'm not sure to understand because like maybe you can explain about synthetic data because like it looks that currently video models knows to generate good or like almost better than real, right? If it's possible, like almost real images that it's very hard to distinguish between an image, artificial image, and a real image. So why you can't just generate a lot of different images, a lot of videos that you can split them to, I don't know, small chunks and generate each chunk separately, um, and train on this infinite amount of data.
yeah, I think that is one of the possible way we can do the data augmentation by the self-generated stuff. But the downside is quite also like quite clear that if your generation is like low quality, say for example, especially the image generation, the text usually is kind of corrupted. The characters are a little bit off. And if you train your model on top of this kind of a little bit lower quality data, your model will accumulate the errors, and again, you train on top of like a lower quality data. I guess your model will just collapse at some point. But I agree. Like, if we can do some filtering and also do this kind of data augmentation, that could be the good, like a good practice to. Especially like dealing with insufficient data scenario.
Do you think that the future will be to collect more high quality data, or we will see something like, I don't know, kind of distillation or thing that, like, I don't know. For example, right, these days all of the models, or all the text models are training and using environments, right? RL environments for different tasks. Do you think this is the future for vision models also?
Yeah, definitely. I think data is extremely important. Like for image, it is, as I mentioned, it's relatively easy to get. But if we want to generate like a multi-model stuff, like say text to music with different models or text to video with different models, how to get a high quality music data? I mean, it's challenging, especially it has like some high quality music data has IP protected like stuffs. Um, and also for the video. And on the other hand, it's more like for the text, in my opinion, it's like we have longer, I mean, human have longer history for the good quality text data compared to video. I mean, how to get the high quality data to train different models is definitely one of the big challenges.
Okay.
Well, what about we mentioned data problems and getting enough quality data. I know that there have been problems when you just scrape such large amounts of images from the internet or even videos where unfortunately, especially historically, it's probably better now. Some of those data sets had illegal content in them. Just, you scrape 2 billion images from the internet, there's some messed up stuff in there. Do you, beyond just like the negative prompting techniques for safety, do you have any thoughts on what we can do to further mitigate these kind of problems?
Yeah, that is actually like a really good question. So in my opinion, like generation and also like how to make the safety in part is equally important. Like we want to push generative quality, at the same time we also want to do it safe in a safe way. One way is like we can do as you mentioned, like do negative prompting to train your model, or you can actually make your model to forget about this kind of dangerous data, uh kind of related to the negative prompting. um and yeah, I mean, there are tons of papers and tons of tricks that we can achieve it. But to my understanding, it is hard to say whether it is like scalable or like can be reached commercial level. So I think it's still a good open problem to think about.
What other open problems we have, or do you think we have in image generation that, like, we don't have a clear path how to solve it? That, like, it's not that, like, yeah, you just put more compute, put more data, tweak a bit, and you will get better models. Like, what fundamental problems we have in image generation?
Yeah, I think in terms of the academic stuff, I think people are still trying to push about good generative models, even beyond diffusions. Say for example, I want to do the generation fast, do the training easy. The controllability is like great, and the sample diversity also great. So I mean, we don't just memorize the training data. Like how to really find such a like a powerful generative model is still like on the hot topic, even for image generations. So
But do you think, like, if we'll take, I don't know, Nano Banana from Google, right? It's quite a good model. Correct me if I'm wrong, but for me, it looks quite good model that most of the time is doing very good job. Do you think if we will take it and scale it up and use existing methods or change it a bit, and 10 times, 100 times, 1,000 times, bigger with more compute and more data. Do you think we will not see there will be a problem that we will not solve?
Yeah, first I agree. Nano Banana is fantastic model. I love it. And actually, I'm curious about whether at what degree it is diffusion based. I have no idea. And definitely, like in terms of this more like commercial oriented models, if we can accumulate more data, scale it up, we at high chance we can imagine like we can get a more powerful model. But at the same time, in terms of research, it's always curious about whether diffusion model is the only thing that can do the job. Whether we have alternative. It's just like how people go from GAN to diffusion. Like before GAN is dominating, but now GAN is kind of a tool to make the generation even better, incorporate with diffusion models. But what could be the next is quite interesting. So
And more personally, do you think that diffusion will be the answer? You know, that, and for example, Jan is very, we need role models, like this is the answer, and now let's ask the question and what we can solve with that. Or even Stefano, I think, is really like, diffusion models are the answer for everything. Do you agree with that, or do you think it will be like mix of different things, or things that like we are not thinking about them right now?
yeah, I wouldn't say definitely diffusion is the only answer, but to me it is quite natural to do the things. Just going back from the more like principles perspective, like generation is just like how to transform from the distribution, the noise distribution to your realistic distribution, and people can do like this kind of one jump, just like GAN. But you can also do, simultaneously, and also mathematically, you can do this kind of step by step, like a transition. So it is actually quite consistent with the like optimal transport perspective, like how you transport one distribution to the other. There are two formulations. One is just to use one function jump. The other one is like you define some dynamics. And I tend to believe this kind of you define some reference dynamic and the adding noise as a reference, and then like a denoising to flow the things is quite a neat way and the right track to think about it.
Okay, I think we're almost done. I want to talk about paper. We talked about it a bit, but it's a great paper, really, really great paper that they just recently published from Stanford, from Fei Li's group and some collaborators. And I would love to hear your opinion about it. So the paper called Mirage: The Illusion of Visual Understanding. And the basic finding is pretty amazing. They show that all the frontier models, the multimodal models, when you ask them a visual question, but don't actually give them an image, right? They just confidently describe an image anyway and answer as they saw one. They describe the image like really the fine details of this image. So they call this the mirage effect. And the crazy part is that these fake answers, they aren't random. Like on medical benchmarks, especially, the models retrain 70 or like 20 or 80% of their accuracy without ever seeing one single image. They also they even trained a tiny parameter, like 3 billion parameters text only models on this benchmark, right? Without any image, and they beat most of the frontier multimodal models, and even human experts on some test data set. So I think this is really raised the question, when these models score so well on visual benchmarks, like how much of this is actual visual understanding versus just these models are really good on exploiting statistical patterns in the text and to detect biases in the questions and things like that. What do you think about it?
Yeah, I think that is an interesting paper. Especially, thanks for bringing this paper up to me. Like, I would say it is evidence showing like we should treat the understanding and the generation as a package. It is a good evidence, right? Like even without any even without any image, like it can do the things quite great. Somehow have the somehow has the like kind of demonstrating like the model is should have some understanding ability. Definitely like if we can build something, based on the takeaway message from this paper and build some like generative models on top of that, that is awesome. Like perhaps we can reduce a lot of image during training. For example, we can just perhaps use some prompt or whatever and recycle it and do the things.
But do you think? I think it also says something more fundamental about our benchmarks, right? That they're quite broken. Like you can know all the answers without the actual images or videos, right? So what's the point in this benchmark? Like,
Yeah, I think benchmark to my understanding is just one facet like a score. It's just like a one how you cut the evaluation from only one projection matrix, right? So we shouldn't really trust it too much, but yeah, I would say like it could be many ways to break the benchmark and yeah.
Do you think that there are any uniquely good benchmarks with diffusion models right now, or do you have like a favorite that you think is especially good?
Yeah, I tend to believe no, because there are so many factors we need to take into account. Um, benchmarking in terms of quality or whatever. Um, the quality also have a different perspective, like whether it's really realistic or whether the text broken in the generation, whether the physical structure of the image is really making sense. There are different perspective of like checking your generation quality. Um, so I tend to believe the current benchmarking is not extremely perfect. Um, so we need to combine different statistics to kind of have a more comprehensive evaluations.
That's too bad. She had a more like upbeat answer, but I think that's just the state of the field right now.
Yeah.
what do you think about simulations? The game simulations and like even like real world simulations. Do you think they're useful?
Yeah, definitely. Like the game simulation or word simulation, pretty much similar to the question that we discussed, like word model. Um, could be useful in the sense like auto driving, for example. Like it should have a real time interaction with the agent. And at some point, perhaps we can play around with game generated by AI. That could be quite fantastic. And like for example, like even the music, background music, the game design or like whatever action you have done in the players are totally decided by AI. That is quite exciting moment, I would say. And on top of that, I guess if we can really make the models work at that degree, we can provide some tools to support the creators to reduce or to leverage their workload. Game design or making the music from scratch is not an easy task. So yeah, just like the other version of ChatGPT for creators.
Okay, you're almost out of time. Do you have anything else that you want to add, that you want to advertise?
Yeah, I think it's like all about the book, the Principles of Diffusion Models. Actually, we are in the discussion with publisher. Um, it should be sorted out pretty soon. It goes from the three different origins of different models in the principal perspective toward the fast generations. Diffusion-based fast generations. And we also have some like supplemental kind of websites and toy codes that will be provided later that can help professors, students, practitioners, whoever, I mean, junior researchers, whoever want to know about diffusion models to get the idea. And on top of that, the discrete diffusion is actually quite related to the continuous one, and the origins and the design space are quite similar. So I think it is a good reference for anyone who is interested in the field. So
Okay, yeah, it sounds good, and it's a great book. I totally
yeah, thank you very much.
agree. Okay, so thank you so much that you joined
All
us
right.
today. It was really
Yeah.
nice to talk with you, and it was
Yeah,
really
thank you very
interesting
much.
to understand more about diffusion. And thank you for coming, and thank you for the audience. And see you next week.
Yeah, thank you very much. Thank you very much. Bye.